I'd like to welcome you on this beautiful day in Cambridge, Massachusetts to the Picture Language Seminar. We have several interesting talks coming up for the next 4 weeks. We have Juan Jones, then David Gross, and after that, Gilles Pizier. And not on the screen, but the week after is going to be Marianne Leitner. And today we're really pleased to have Paul Fendley. He's now at the University of Oxford since 2014. He was a graduate student at Harvard of Paul Ginsparg, and then spent a number of years at the University of Virginia and other places before going to Oxford as professor of physics and senior research fellow at All Souls College. So Paul is going to tell us about integrability, braided tensor categories. Paul, we're looking forward to your talk.
Oh, well, thanks, Arthur. It's really an honor to be giving there. I wore a shirt with a collar for the first time, I think, in 3 months. So what can I say? So anyway, let me share screen. There we go. And then let's go to full screen. All right. Everybody hear me? And Arthur, we're good?
Great.
Okay, so let me get rid of this. Okay, so actually the title, I realized, just slightly changed from what I gave you. I said, I hedged when I gave Arthur the title. I said integrability and braided tensor categories in the title, and then I Freudian slipped and said from. And when I get to the end, maybe I'll try and say what the distinction is. Anyway, this is a project that has gone on literally, I don't know, for 8 years or something like this, but I honestly am writing the paper now, and hopefully within a month. And I want to put in a plug, and I'll say a little bit more later on about a epic paper that is really almost done, as in a day or two, hopefully. A long paper on closely related stuff with Dave Ossen and Roger Mung. We wrote part 1 4.5 years ago, but the full general one will be appearing soon, I hope. So, how do I have to do it that way? Okay, so the general theme of this talk is to explain how statistical mechanical models can be viewed by using tensor categories. And it's this spectacularly beautiful story, and it was a big thing in the late 80s. But it kind of got forgotten for lots of good reasons. People moved on to other stuff. But in a world where maybe I don't quite live, but where I talk to a lot, is condensed matter physics. And 10, 15 years ago, people got very excited, especially those at Station Q, like my collaborator, Dave Ossen, and in topological quantum computation. And this got a lot of people in that world very excited about knot invariants and all this classic work of the 80s. And my angle on this then is that I want to apply to statistical mechanics, which is obviously related to condensed matter physics, but not the same thing. And so the key mathematics I exploit is that tensor categories give a consistent set of relations that allow graphs to be manipulated without changing their evaluation. And the moral of the story, since this is the mathematical picture seminar, right, is to draw pictures. And this slide was made, I think, several years ago. So I did not add that for Arthur's benefit. In any case, so here's what I'm going to talk about. I'm going to talk about, tell you what fusion categories are, since maybe not all of you know, and tell you what they're good for. I'm going to tell you how to then define these lattice models using them. And these are the types of lattice models, and that's flashed for people who know that already. I'll explain what these things are when we get there, except I won't say anything about quantum Hamiltonians, but everything I say can be ported over to that case. And then the next thing, kind of where I want to bring some integrability into the story in the stat mech models is I'll explain to you again how the Yang-Baxter equation fits into this story. And then I'll generalize the categories. If you see up here, I said fusion categories. I want the pen to work. I don't know why it's not working, so hold on a sec. Draw. So no, is that working? It was working 5 minutes ago, so that's annoying. Oh, there we go. Work now? Yeah, it should be working. Oh, there we go. Okay, good. Sorry. So anyway, so I mentioned this was fusion categories, and that's how I would define the lattice models, but then I'm going to introduce more structure. Ah. Sorry. Why is this? Oh, jeez, I don't want that. I started subtitles, so, oh, jeez. So how do I, that, there we go. Sorry. Anyway. So I define them using fusion categories, these lattice models. I'm going to define them. But then I'm going to tell you how to use a more object with more, a category with more data, with braided tensor categories, to do the main thing I want to do in this talk, which is explain how to do Baxterization via fractional spin conserved currents. And if you don't know what that is, that's the whole point of the talk. And the upshot, the answer to the conclusion of this talk is I'm going to give a simple formula for the Boltzmann weights in terms of this category data. So this is the payoff for all the work I've done setting it up in the previous parts of the talk. And it'll guarantee the existence of these conserved currents. And then the beautiful thing about it is that having found these weights by this equation, they also satisfy the Yang-Baxter equation, which is the key to integrability. And the reason why this is a good thing is because the Yang-Baxter equation, as I'll show you, is rather nasty. And the equation I'm going to show is much simpler. In fact, I can solve it. And so that's the point of the talk. Okay, so let us proceed. So this is part one, what the fusion categories are. So it associates a topological invariant to some kind of thing I call fusion diagram. So what a fusion diagram, I think that's my name, I don't know, maybe someone else named it. So what it is, it's a labeled planar graph. So that's the thing over there. So it's some graph you draw with trivalent vertices, and then you label all the edges in the graph. And that's what I'm going to call for the rest of this talk a fusion diagram. And so where the category now comes in, well, it comes in lots of places. Where it starts to come in is the objects in the category, the thing you're building the category from, are labeled A, B, and C. And that's what you label the edges with, Greek or Roman, it doesn't matter. And so now where the category really starts to come in, so you build the category from a fusion algebra, which says you take the tensor product of the objects in the category, and it gives you a linear combination of other objects in the category. And then there's these non-negative integers and ABC that tell you how many times the object appears in this tensor product. And so most people will be familiar with tensor products of representations in Lie algebras. For reasons I'll say in a second, really for this, you probably want to think about quantum deformations. But from the point of view of the fusion algebra, you just tensor two things together, you get something else. And the integer coefficients just tell you how many times it appears, 0, 1, 2, 7, whatever. And then in the picture, so I've got a picture up on the top here, but then we build it from these vertices here anytime you have a non-vanishing coefficient. So now, I said, so what the category does, the fusion category does, tells you how to get a number out of that picture. So I draw that picture, I label everything, and this is the data that the category gives you. So it gives you the objects, that's these A, R, S, A, B, T, T prime in this picture here. Then there's two kinds of objects. There's the quantum dimensions and the F symbols that I've gotten written up there. And So let's, now there, okay, so here's the two key relations. I'm just skipping tons and tons of important and deep stuff, but I'm a lowbrow physicist, so I just get to use all the hard work mathematicians put into these things. And so one of them, one of the things I use is if you ever see something that looks like this picture here in your category, in your fusion diagram, sorry. Why? Is this, you can get rid of that bubble in the middle by, so this is this bubble here, and you remove the bubble and you get that straight line there. And those you multiply those numbers, the delta AB tells you the two ends have to be the same. And so for example, if you set A and B to be the identity, so that's just no edge whatsoever, you just get a circle and then you evaluate. So sorry, that should have had a R there. Okay, so that's the easy one. This one is almost as easy. So this is what in this racket they call an F move. If you're familiar with 6J symbols in quantum mechanics or Lie algebras, this is a glorified version of that. So if I have a picture like this where I've got two trivalent vertices and all their labels, what I can do is replace it with a linear combination where I've re-glued the line in the middle. And these are the coefficients. These are just numbers. And again, I say I'm a lowbrow physicist, so I'm just taking this stuff. This is handed to me by mathematicians telling me category. And by manipulating any planar graph like this, you can just simplify it, and you end up getting a number. I mean, it's a complicated number because this is a sum over here. The F symbol, this relation here is a sum, but it's a number in the end. And that's what one of the things a fusion category is good for. Okay, so here's an example of something that you can get with fusion category. So this evaluate this. So you would take, say, do an F move. I guess the way I did it here, you would do an F move with these four, and then I would sew it. I get a bubble. I remove it. That's why you get the quantum dimensions. And you blah blah blah. You keep going, and this is what you end up with for that picture. Now I could have started with a different F move, and I would have gotten a different answer. Now, but the point is consistency says that these things have to be the same. So, well, they're the same. And so that gives you lots of identities. Now, again, there's much more complicated things. A very famous one is called the Pentagon equation, which I wouldn't even write out all the indices, but basically you have a equation in the form FF equals sum of FFF, and there's lots of indices and you're summing over things and all that. Anyway, so that's an F move. And the fusion, I saw someone said it's called a Whitehead move. I did not know that. That's interesting. Anyway, and again,
sorry.
to emphasize, yeah, sorry, question.
No, it's just a remark. It's indeed a Whitehead move. It's very well known thing in like topological graph theory and in geometry. So that's why
No, thank you. I swear I didn't know that. I guess I hang out with the wrong people. Good. All right, it's a Whitehead move, but I'm going to call it an F move today. For obvious reasons, we use F. Not a very good name for it, but that is the name we use. And again, the thing I just put, the category for me today is input. I'm not going to say anything new about categories. I am going to say something new, I hope, about lattice models. All right, so now I'm going to tell you how lattice models come from fusion categories. And I should say the story begins well before any the word fusion and category, I think, were ever put together. It goes back at least to work by Temperley and Lieb, or at least the connection to lattice models, I should say, goes back a long way. And so what they were doing back in the day is what they did is they took they took some lattice statistical mechanical models, they wrote them in terms of the transfer matrix, and then they showed that you could write the generators of the transfer matrix in terms of these things that satisfied a very nice algebraic relation. Now it's called the Temperley-Lieb algebra. This is where they discovered it. And this made you could prove that lots of different models were consistent, including models that you make using graphs. gas. And that's where the fusion diagram is. And those names down there can ring some bells for people who've heard of some of this. So let me talk about now what's kind of the basic model of all this. And it's easy to define. In fact, the category you'll see makes it look more complicated, but there's a payoff. So this is now what, depending on who you ask, gets a different name. It's called, I usually call it the completely packed loop model through these equivalences that I just briefly mentioned. It's got some other names as well, but this is what it is. So the degrees of freedom are loops on a lattice. That's these things here. So those are the loops. And the completely packed means every edge of some square lattice here. The dots are the dual lattice, but every edge is covered by some loop. But the only rule is they can't cross. So at every vertex, you have a choice. They can avoid horizontally, like I just circled, or they can avoid vertically, like I just circled. And so that's your choice. So that's your degrees of freedom. Just everywhere you choose, you sum over all possibilities. So you just, at each of these vertices, you make one of these choices. And so you then get loops if you choose the boundary conditions, right? And the partition function, the things that make people like to compute, says you sum over all the loop configurations that you get by drawing this, and then you weight them. So D is some number, and you take D to the number of loops. So it's a weight D per loop. Again, hopefully that's ringing a little bell with what I showed you a few minutes ago. And then these are the local weights. So I should have written that down, local weights. So V and H are local weights. And what that is here is up here is just the number of crossings and the number of crossings. Sorry, the number of avoided crossings of each type. So, so that's the loop model. And then just to say the general form of the weights here, sorry, the partition function here is you've got a topological weight you've got a topological weight, which is the D to the loops. So that's topological. And then you've got this local stuff, which is the number of the avoided crossings of the two types of avoiding. And that's the generic form. For general categories, the weight gets more complicated than counting loops, but that's the general form of these models of all of them. Okay, so let me write this out now to try and start making contact with this fusion category stuff that I told you about a little while ago. So we picture the loop model weights on the square lattice. And so what I do is now I draw a picture. This is the square lattice. And to summarize this two kinds of avoiding in the local weight, well, I take this. So that's just the potential crossing. And then I decompose it into these two crossings there. And to parameterize these local weights, since there's only two of them, overall parameters don't matter. There's really only one parameter for these two. And I'm going to call that the spectral parameter for non-obvious reasons so far. It's called the spectral parameter U. And then to get the same picture of that we get in the category what we do is we take all these, and so what it means now, so what this picture means, expand out each vertex and to get these loops by that picture up there. So expand each vertex, you get all the loop configurations. Each configuration, you count the number of loops, you get the weight D per loop. And so all this page is a fancier way of writing what I wrote on the previous page, but now one that hopefully starts to look like doing things in categories. So I could just stop there, and most people that analyze loop models do it just by just loop models by writing out in terms of loop, but I'm going to be perverse. I'm going to write them out in terms of something much more complicated. So you take the fusion category, which goes by the name of SU2 level K, and if you don't know what that is, I'll just tell you the few things you need to know for this talk. There's K+1 objects, which I label in the physicist manner, which is like spins of SU2. And so 1, 0, 1/2 up to K+2. So that's the labels of these objects. And the reason I do this is so then I can just remember how fusion rules go. Hopefully people have seen, take a tensor product of two spin-1/2 representations of SL2, the algebra, and you get the identity. So 0 is for me always the identity plus what physicists would call the spin 1. So now I didn't write out all of them because it's actually, there's this truncation here. So it's not the same as SL2. Various reasons. This is why I mentioned before it has something to do with the quantum group algebras. But I won't need that. I'm just going to use the category data. And here's something. And okay, so the lines, so now I'm going to do the picture. The lines making up the loops in my picture will be labeled by this object 1/2. Okay, so, and then when two lines in the loop model meet, what I told you above, well, they avoid either vertical avoidance or horizontal avoidance. Now in the category though, because I've got this relation here, oops, sorry. Now let's go back. In the category, when two lines meet, they fuse. Sorry, that got awfully low. Hopefully people can see that. They fuse, either they can fuse into two spin-1/2 lines, can fuse into the identity, which is the picture on the left down here, or they fuse into the spin 1 in physicist language object. And so, okay, so that looks good. So we've got 2 up there and we've got 2 there. But the catch is, of course, when I'm drawing these pictures in the category, I can draw them that way too. So it looks like I've got 4 of them. It looks like I've really confused matters further. But the nice thing is the F moves tell you that there's relations. And this is what they happen to be if you work out what the F symbols are, these coefficients are in this SU2 level K category. So those are the numbers over there if you care. But more importantly is what I can do is I can take any of those 4 things I had on the last slide. There's 2 linear relations that relate them. So that means I can write degrees of freedom in terms of loops if I want, or I can use these squiggly lines, the spin 1 lines. I just made them squiggly so to single them out from the other ones. And so you can write them any way. Now loops are a perfectly good basis, but there's advantages to this one, and we'll get to that later in the talk. So that's why I want to do it. So let me advertise. That's right, what I said. So okay, so the advantages of writing them out in terms of these squiggly lines instead of just loops. Well, first of all, it makes it sort of natural how to define these geometric models, what I call geometric models, for any category. So remember I wrote down this form, Z is the topological weight, times the local weight. Well, you evaluate the graph, a more complicated graph, and then multiply it by some local weights. But a really major advantage now is once we do that, we can relate all these geometric models where I'm drawing all these nice pictures in the mathematical picture seminar. I can rewrite them in terms of local models. So I'll tell you a little bit how that goes, although I won't give much detail on that. And then another thing is there's then lots of new properties you can define. So anyway, right, so let me tell you very quickly how do you get a local model of it? And so I'm going to give very few details, but it's really important, and this is really an enormous advantage of this. These local models, if you just define them by brute force, are nasty. So basically nothing I'm going to tell you in the rest of the talk you can actually do for local models. Even icing, you can do a few of the things. Everything is too hard, but when you set it up like I'm setting it up, it becomes essentially no more difficult there. So anyway, so the heights, these are like heights or spins, live on the graph that's dual to the fusion diagram. And then there's a formula that says anytime I've got a fusion diagram and I evaluate it, I can alternatively evaluate it by summing over these local Boltzmann weights coming from these heights, these spin degrees of freedom. And this is this classic work. That's what Temperley and Lieb were kind of doing at the beginning. That's what a whole series of people, and this is best known in the maths world, I think, is Taraya Viro construction, although now I think we call Derive Vera Barrett-Westbury, who made some crucial things, but all the other people had absolutely essential place in the role. So what it tells you is you can turn these non-local models, these geometric models like the loop model. A loop model is non-local because you have to look at the whole system to decide whether how many loops you've got, because a loop can stretch all the system. But the weights here up that I define there, that's all local data, if you look at that more carefully. So that's a remarkable simplification. And so that's why everything I say will be working. And if you want an answer, that's what it looks like for this temporally lead case, the loop case that I was doing. That's part of it. Okay, so now, okay, I wanted to put in a very quick plug for the work I did with Dave and Roger that I advertised at the beginning. And this is another thing that's here. So, this is just completely a shameless advertising for work. So what we can do in this paper, what we do in this paper, is give a very systematic way of defining, oops, didn't want that, sorry. A systematic way of defining topological defects on the lattice. And this gives all this universal information. In particular, it allows you to generalize Kramers-Wanier duality to a whole host of models. It's really really a beautiful story. And then you can compute universal numbers, you can compute exact degeneracies, all exactly on the lattice, actually, and rigorously. The only non-rigorous part is if you want to compare it to what you might get in a continuum field theory, like a conformal field theory. So we can get these conformal field theory spins on the lattice. Ours is exact and rigorous. The non-rigorous part is if you want to match them on to the continuum theory, but on the other hand, it then provides a constraint. So that's an ad for what we do there using the fusion category. All right, so now let me get back to my story. Which is the following. Okay, so what I've done so far, let me pause. Okay, let me summarize what I've done and then I'll pause for questions. So what I've done is I've defined very quickly a fusion category and showed you how you use it to get numbers from fusion diagrams. And then I showed you, at least very quickly, I hope it was enough to at least give the idea, how you define lattice models like the loop model using this data. And the next thing I'm going to do, you can see from the slide, is tell you how integrability fits into this picture. And then I'm going to use it to compute these conserved currents. But I'll stop for questions now, since this was, this is a good one.
Your talk reminds me a lot of the talk we recently had by Cheng-Wei. Cheng-Wei, do you want to comment on the connection?
Well, not yet. So far as the classical work, I'm looking forward to the new results.
Okay, good. Yeah, yeah, because he was talking about quantum stuff, which this is all closely related, but not the same. Well, yeah, all my Station Q friends, want to do the 2D quantum case. I'm doing 2D classical, and I'm going to stick with that. But there's still plenty of stuff to study. Good. Any other? Well, I'll move on unless someone interrupts me. Okay, so this is the Yang-Baxter equation. This is the key to integrability. So again, a huge story. The form I'm giving is really Baxter's work. Yang played an essential role, but the way I'm describing it is the Baxter version that he used to exploit and compute so many things exactly. Just a spectacular result. So what it is, it's a relation. So this picture here is really all there is to it. Once you get there, it just says you take these Boltzmann weights I've defined by these pictures and you put them together in this fashion. And so this parameter here, if you remember, is the spectral parameter. And that's just, so it's an equation that parameterizes, it's a 2-parameter equation. So there's 3 Boltzmann weights, but you see there's one linear relation between the parameters. And so we, what is this? And there's one linear relation between the parameters, and there we go. And so if the Boltzmann weights satisfy this is the beauty of it. You can construct transfer matrices that commute with each other, and when you and they commute at different values of u, That's why U is the spectral parameter, because it then the eigenvectors don't depend on U, and so only the eigenvalues, the spectrum, depend on U, hence the name spectral parameter. And so notice the key thing is in the left and the right, U and U prime have swapped places, and that's how you compute the commuting transfer matrices, and then you get this local conserved currents, and that's what gives you integrability and lets you do all sorts of exact computations, exploiting meromorphicity in U and all this great stuff that Baxter does. But that's the equation. So we're just going to view it as an equation. We want to solve this. We want to find Boltzmann weights and solve it. And it's not easy. Let me just draw quickly. This is what it looks like if you want to draw it in terms of the height variables. So it gives functional equations to just to show you how nasty it is. This is the simplest case I know of for solving the Yang-Baxter equation. And so it's for the loop model and all the local models that are associated with the loop model. So you plug in this ratio of weights, H over V, because it doesn't matter what the thing. And so that's your nasty functional equation. Notice you've got these bilinear terms, you've got a trilinear term, all different arguments. And you can muck around. I mean, since it's so wildly over-constrained, if there's a solution, you can usually find it quickly once you get to this point, if it's not too bad. And of course, people found it. There's the solution. And it's really simple. And so this seems like a whole lot of nastiness to get something that's pretty simple at the end, a very simple ratio of very simple trigonometric functions. I just adopted the usual parameterization for the spectral parameter U. And as I keep saying, you can do this for local models with not much work. Okay. But then the next thing is, I mean, how do you get something so simple from this complicated equation? All right, well, those of you who know something about braiding already thought that's familiar. Even actually so let me bring in braiding to the story, and I'm going to be an almost insultingly lowbrow perspective, is that from my very crude point of view, what Jones showed is that you can take this temporally Lieb algebra, this SU2 level K-fusion category I showed you a little while before, and you can get representations of the braid group from it too. And what that does is let you get not invariants. So what happens when you've got a not, when you've got a not invariant, you project it onto the plane, and then you get overcrossings and undercrossings like that. And then you have to compute the not invariant. So that's an old story, and it's spectacular. And here's how it works in this language. So we've done some work, and so we do it. So for the Jones polynomial, the very original one, so what you do is called a skein relation in general. This one I think is called the Kaufman bracket, and basically says every time I have an overcrossing, I replace it with this linear combination. And every time I get an undercrossing, I replace it with that linear combination. So, and then what I do is exactly what I've been doing all along. You stick that and you get a sum over loops. And then to get the Jones polynomial, you evaluate it by replacing each loop with this number. That's all. And then that gives you up to one subtlety I will tell you about that gives you the Jones polynomial. So let me show you now why this works so beautifully. So of course, like with the fusion category, there have to be lots of consistency relations. So this is one of them. So I've taken a braid, an overcrossing, an undercrossing. So obviously topologically, I could have dragged this guy through and nothing happens at all. But if I plug in this thing, I get the nothing at all that I want, but I get these other things too when I plug in what was on the previous slide, this linear combination. But the point is, I can get rid of that. By using this rule that you remove closed loops, and then all those bits cancel and I get what I want. So it's really beautiful. Now, like I said, you couldn't fail to have noticed that the Yang-Baxter equation looks an awful lot like the third Reidemeister move. In fact, sometimes in the literature, you see this thing called the Yang-Baxter equation, which I want to emphasize is wrong. The Yang-Baxter equation, as written by Baxter at least, has these two parameters. So it's a functional equation. a two-parameter functional equation. But the resemblance is obvious, and in fact, back in the day, people observed, including for the case, I've shown you the loop case, that you can obtain a solution of this braid group relation, the third Reidemeister move, by taking a limit of the weights. And it turns out it's I plus and minus I infinity in the conventions for U that I use. So, you know, anytime something as spectacular as this happens, post-Jones, a lot of people did this, but there's one, a lot of people studied this, but there's one catch that people noticed at the time. In fact, it's a key thing in Jones's paper. All right, there's the first Reidemeister move, which is the simplest one, just one strand looping around itself. Well, topologically, that's the same because it's just depends on the projection. But if you plug in what I just showed you, this, you take the overcrossing and replace it with this linear combination, well, you get that back, but you get this annoying phase here. And well, what do you do? So this comes up in, I mean, in Jones' original paper. I mean, you have to get this straight. And then to undo it, you frame the knot, so you make each knot into a ribbon. And then when you, this thing up here, you see this, the twist around corresponds to twisting the knot by 2 pi, and that's called the writhe. And so you have to undo this. So I think it's fair to say for, you know, the original interest in the knot polynomial, it's a pain, but for, well, I said it's a feature. This is exactly what we want for what I'm doing. So this thing, so in a way, the braided tensor category is a much smarter object than just the braid group. So it's got that. So what we do now is define this braided tensor category. And so what is, you take a fusion category, all the same, you've got the fusion, you got the quantum dimensions, the bubble removal, all that stuff, but we've got one more thing, and that's if you twist that thing around. So it's a braid, well then attached, where you then glue the two ends together, and then you untwist it. So I guess the way I defined it, that's a left twist, probably backwards from the way it ought to be. And you get these factors. Now the factors omega are just, well, in a fusion category, the spins S sub A are rational numbers. So the omega are roots of unity. And so you just get these roots of unity, these twist factors, we're called. And then you get these annoying things, these nus, which were the bane of my existence. And so I'm going to take prerogative of the speaker and just forget them. They're there, you can follow them through all of this. They're just a pain. So anyway, so that's where you get, you twist, you do the braiding, and then you twist this around, and then you go. All right, so that's all you need actually, is these twist factors, the omegas, because then you can get braiding using this. So that's just, I'm going to flash that to show that you don't need to define the braid matrices. It's all already there once you define the fusion, and there. That was quick, but I hope it gives you the idea. All right, so now I really want to get to the heart of the talk, and then I can tell you about my results, which luckily I've spent a lot of time setting up, and then the results are pretty easy to say. So, okay, so Jones did this spectacular work, including this subtlety I just told you about. And then there was this connection to StatMech that I mentioned at the very beginning. And people wrote lots of papers, all sorts of nice stuff. But then Jones said, well, let's go the other way. Let's coin this verb to Baxterize. And that means to start with a not invariant, or if you want to say maybe a little more generally, with a braided tensor category, and then try and generalize to a solution of the Yang-Baxter equation. So you put in that spectral parameter and then get a lattice integrable model. So, so that was Jones's idea. You can do stuff by brute force. People have. it turned out most of the models that people studied, the integrable people, especially the Kyoto group in the 80s did this. Well, sorry, I should say the Leningrad and the Kyoto groups in the 80s did this, all this spectacular work. So most of the interesting examples, I think they just worked out by being smart and careful and knowing some stuff. So brute force is doable, but well, if you've ever tried it, it gets horrible. At least the simple ones people did. There was some success in a more general approach, and this used quantum group algebras. Jimbo gave some conditions, and then a few years later, Australian group, Jangold, Bracken, and then some later papers with Delius, gave a general formula, in fact, that I'm going to tell you what that formula is. But the thing again that strikes me, if you look at this work, which is pretty technical, involves all these intricacies of representation theory of quantum group algebras, there almost none of the quantum group ends up in the formula at the end. I'm going to show you the formula. So remember this statement when I show you the formula. So again, like I said, with the solution of Yang-Baxter, all this is showing there's still got to be a better way. And I'm trying to get there to the better way. So finally, this is now the heart of my talks. Pretty much everything I've said for the last 42 minutes is review, maybe done through a filter, but review. So now I'm almost to the new stuff, but I got one more slide here. And so there's a whole story that I won't tell you much about why they were doing this, but Smirnov, as part of his Getting the Fields Medal, defined these non-local operators in lattice models, and he called them discrete holomorphic. In the Ising case, the fermion operator, it is holomorphic in the sense that it obeys all the needed lattice Cauchy-Riemann equations so that he could prove that in the continuum limit, it became the holomorphic fermion field in the Ising conformal field theory. So this was how he proved, rigorously, mathematician proved, that the Ising lattice model becomes the Ising conformal field theory. And so buoyed by the success, he wanted to do other ones. And so he found a bunch of examples, but he could only show that they obeyed half the lattice Cauchy-Riemann equations. Being half holomorphic is like being half pregnant. It's not, and so it doesn't work for what they wanted it to do. But it does work for something else, and this is what Cardy pointed out. So Cardy and his collaborators found lots more examples of these beasts, these things that satisfied these equations. I'm going to write down what the equation is. But what they said, let's think about it in a different way. And I'll make this point again, but I wanted to say it in advance. They said, let's look at this discrete holomorphic relation. And I haven't told you what it is yet, but let's look at this relation. What it turns out, if you don't fix the Boltzmann weights in the beginning, it gives you a linear condition for them. And you solve it, you get some Boltzmann weights. They showed in lots of cases you could generalize what Smirnov did and find them. But then when you solve it, it's a much simpler equation to solve. And the Boltzmann weights you get also solve the Yang-Baxter equation for free. Didn't have to do anything else. And that's just a check, that's not a proof, but it did do it. So I'm going to explain now all this category. I spent 40-something minutes explaining, gives you the perfect setup to generalize everything Cardy and Smirnov did in this language, and generalize it to local models. And then I can actually even just solve this linear equation. I still can't prove the Yang-Baxter solutions, but I can prove it. All right, so this slide is literally just review of everything I said before, since it was a while ago. In the loop model, what we did was have the top equation. We put both the avoidances into one convenient thing with the local weights multiplying them. I didn't write out the second equation before, but I said it in words, so now I wrote it out. In a general category, what you do is you sum over all these trivalent fusion channels, if you wish to call them that. And the A's, there are the amplitudes that generalize the V and the H. And they can depend on more than one parameter, but I'm just going to write them in terms of the one parameter. And then the partition function means you stick in that sum over Boltzmann weights, you expand it out, and then in the more complicated case, I get some complicated fusion diagram, which I have to evaluate. And then these local weights, these A's, these amplitudes, whatever you want to call them, are there for every vertex. So V is just each vertex there, and boom, there you go. So that's the review of what we did before. And again, I think last time I showed in local models, this all works for local models with almost no more work. All right, now this is, well, my version of what Smirnov-Carty and collaborators were doing. All right, so we've got our graph there. So ignore the green dashed line for a second. All right, so again, if you ignore that, it's the same picture I had on the previous slide. But now I pick another object that's called phi, that's in the tensor product of row, tensor row. And so what that means is we have a vertex, row, phi. And so all those lines in there are labeled row. I didn't draw all the labels. And now what I do is I stretch that line between 2 points on the edges. So I've got the vertex here on where the W is, and I've got, let's get the pen to work this time. There we go. So there's at location W, there's at location Z, and I stretch it before because I have braiding. I can pull it out of the plane if you wish, or define it in the plane via the skein relations I showed you before. I need a braided tensor category, but that hands me the skein relations. And then I evaluate that beast. So I still evaluate it like I did for the partition function, but I include that there. And that's all it is. And so this is a non-local object, and that's the definition card. And all of the definitions that people gave before are all special cases of this general thing I just showed you. What's nice is because of the braiding and the relations the tensor category satisfy, the Yang-Baxter one and all that. Or sorry, I shouldn't say the Yang-Baxter, third right, I must remove. They're independent of path, except when the path twists around. So for example, you get this phase here when you do that. And yeah, so notice what I've done, you can think of this as sort of flipping this over the plane there. So that's a definition. Okay, let me just tell you very quickly what this definition is in the loop models. Because of this condition that follows from the bubble removal thing I wrote long ago, tadpoles always vanish. So if I ever have a line there that ends in a loop, it must vanish. Just look at the bubble removal I wrote a while ago. That's zero, has to be zero. So what you get when you do loops here and you do that there, it just says that the weight is zero unless the string connects the two points on the same loop. And this, I think pretty much every example that people worked on, I think there's a few exceptions, are variations on this template loop. You make it dilute, you do all this stuff, but I mean, it basically all boils down to what I just said. But again, the category gives you lots more things you can do, and so let's do them. So, okay, so now the discrete holomorphicity condition I'm about to show you when I advertised what Smirnov wrote down. So the first time I think I gave a talk on this, which was in 2012, Denis Bernard was in the audience, and he sneered when I described what discrete holomorphicity was, because he said, this is just a condition for the conserved current. And he showed me this paper Giovanni Felder wrote in '91, and that's the equation. So if you remember, I'll just go back one page. These things, well, maybe two, these things, well, we can do this. These things ended on the edge here. Well, look what he wrote. They were doing this quantum group stuff, and then this relation here is conserved. So, okay, so Denis drew a picture. And this is the conserved current relation. So you take this J, I fix the other end somewhere, and then I just move it around. So if you wish, that's one location there, one location there, one location there. And of course, these are all attached off at the other end to the same point, but then I demand this as a condition on that expectation value. And this is the quote discrete holomorphicity relation, but if you write it like this, it's pretty obviously vanishing lattice divergence, which you use to then get a conserved current. So that's the relation that they wrote down and solved by brute force. So to summarize what was going on, so what Smirnov did was he took the Yang-Baxter equation, he took some Boltzmann weighted solution, and then he defined these objects, defined this currents there. in a manner equivalent to the way I described. And then he showed that there were solutions and said some interesting things about them. Now, Carty and collaborators sort of the opposite way. So they defined the currents and said, can we find Boltzmann weights that satisfy this equation, this linear equation? So let me write this out again. It's linear in the Boltzmann weights. Only one Boltzmann weight appears in each. And then they solved it by brute force, not that hard, because it's linear. And then they found just, there we go. Okay, but so we can do better, because not only can we write down the relation in general, not only can we write it in these local height models, but I can actually solve it. I can basically, or I should say, find things. So let me, good, yeah, good, perfect. 2 more slides, because I just give the solution and call it quits. Okay, so again, to remind you, so what you do, so this thing is that, it's the sum over, when you have this collection of Boltzmann weights, it's the sum. So what I do when I take the conserved current relation in the previous slide, so show that again with all my scribbling on it, but it's that linear relation there. So I pick one of those terms, so say that, okay, so I do that, I expand it out, so now I've got, there we go. I've got that vertex there, and then I can do an F move. So you see here, I've done an F move to move that there. That's an F move. And I can do this one, and I get another F move. And I notice I've made them look the same. So I'm writing them in the common basis, to go back with what I talked about a long time ago. When you get these pictures, you can mess around and find a basis. All right, so this one is the most fun. What you do is you take it, you twist it around, so you pick up that factor omega. I then do an F move to move it down to here, and then I twist it back around again and get more of these twist factors omega. So I get this thing here. That's all. I have not hidden anything other than those stupid Frobenius Schur indicators, those news I threw away. That's the only thing. Those would be going along for the ride here, just muddy the equations. But they're there. So that's it. And now, okay, so I've simplified. And then what I get when I do this, okay, so there's the conserved current relation. I do this for all 4 of those. And then you get a bunch of things where the current is going around the center. And then these are some coefficients that I got in terms of the F symbols and all that. And what I need to require for that sum to be 0, taking everything in both sides of the conserved current relation, I have to make that vanish. And then what you find is just stunning. Okay, all the F symbols cancel, only the news left, and that's the solution. I mean, that's really it. So there's a solution. The 1K, okay, so I got the amplitudes. That solves the equation. If the amplitudes obey this, there is a catch. Okay, so that one is easy. That one's by definition. Those are all in the tensor product of rho times rho, and they can be the same or different. It's all there. But here's the catch. I need that to be true. So sorry, I say this equation holds for all A, chi, and phi such that they fuse together. And so that's not a guarantee. So this is a consistency condition for, I shouldn't say you can call it consistency condition. Sorry, we call it a constraint. So you have to satisfy this equation, the one over here, the one in the box, for all n phi a chi non-vanishing. But okay, it works. You can do it. That's the relation again. I just wrote it again. And so this was the quantum group result of Zhang, Gould, and Bracken that they got. Basically, Jimbo wrote down an equation using quantum groups. And so this, first of all, generalizes it to all braided tensor categories. Don't need any quantum groups or pretty much know anything. There, for reasons I don't quite understand, but I mean, when you sort through what they did, they assume a particular phi. It's the adjoint in their case, and this works for any phi. But the thing that makes me happy is no quantum group representation theory is needed to get this. So the thing I said a minute ago, let me emphasize again, a solution is not guaranteed. You have to check that all the ratios are consistent with all. And so there's lots of cases, I can find cases where it doesn't work, but lots of solutions exist that pretty much everything do. I think I probably have ones that, certainly ones that haven't been written down, whether people know about them. You know, Kolya Reshetika knows everything. So I would be stunned if I could come up with one that he didn't at least know was possible, but I haven't checked everything. All right, good, so that's the relation. So let me go to the things I want to do. All right, so these are the sort of not gaping, but the things that I think pretty obviously would be nice to do. So in this quantum group case, the formula of Jimbo, Zhang et al., it would be nice to prove that these weights always give a solution. They can do that in their case because they have all the stuff going on with the quantum groups, and I haven't done, well, I'm not saying it's impossible, it's just I haven't thought hard about it yet, so that would be nice to do. I would bet that's true. The physics, I should say, the sort of intuition behind that, well, if you've got a conserved current, that's a very strong constraint, especially these fractional spin, the things that you pick up this funny root of unity when you twist them around. So, I mean, that's a pretty strong constraint. So if you can get that to work, it's not maybe so surprising you get Yang-Baxter work, but obviously that's not proof. There's this thing I mentioned at the very end that doesn't always work, but I'd like to believe for any choice of row, you can always find a phi. I don't know that's true. I don't have any counterexamples yet, but I don't know if that's true. Most of the resulting models are critical. There's deep-rooted reasons why that's true, but I have no idea how to generalize these to more complicated integrable models. And we can relax the constraints and maybe just finish saying, okay, there's these fusion categories that don't have braiding, but you can always do something fancier, make a category called Drinfeld center associated with any fusion category exists. And in fact, that was kind of one of the key technicalities used in this to make matters nice in the paper I'm finishing with Dave and Roger. So that was really exciting because these weird categories, and Hagura category is one of them. That would be really exciting and new if this worked. Or if it didn't work, it would be kind of interesting to understand why it works for all the other cases, but not this one. Okay, thank you very much for your attention. I'll stop and answer questions.
Thank you very much, Paul, for a very stimulating talk. I'm sure there's going to be a lot of discussion. Yes.
Okay, can I ask a question?
Yes, please.
Hey, hi, Paul, this is Zheng Han. So
Hi.
I have two questions. One actually, so the first one is, I don't quite get it. So are you saying the, parameterized Yang-Baxter equation, well, your Yang-Baxter over have parameters, the same as conserved current relation at a certain?
Well, no, I'm not saying it's the same. I think my hope, I should say, is that any time, okay, all the solutions, all the trigonometric solutions of Yang-Baxter we know, all have something to do with a braided category, whether you like it or not, because they have something to do with the quantum group. So they all exist. I'm saying, I believe for all of these cases, I can find this conserved current for the identical choice of Boltzmann weights. So it's hard not to believe then that all the ensuing solutions of Yang-Baxter will be required, but that's not a proof. So I believe that, so in the sense, I guess the answer to your question, if you believe the sense in which I'm thinking of the Boltzmann, these are equations for the Boltzmann weights. I'm saying any solution of this linear conserved current relation will also solve the Yang-Baxter. Any solution built using a braided tensor category will then also solve that. But that's a conjecture. I don't have counterexamples, but
Okay, so that's my second question is, actually, when you define your conserved current J, so you choose to be all the braiding or overcrossing?
Yeah.
I assume actually there are many choices you can make. There are 2 to the n choices you want to make. You can be overcrossing or undercrossing. But I think this might be related to your last item on your future direction. So many of the fusion categories, although they are not braided, they are half braided, which means that you can define the overcrossing, not necessarily the undercrossing. So I think there's a possibility that actually, your theory can be generalized to fusion category using only half braiding rather than the full braiding.
I totally agree, and I hope so very much. People are, I hugger up is where I run out of gas, but there's people out there who know hugger up much better than me, so I'm hoping they try. But yeah, what's striking to me is the answer is the answer is so simple, and I didn't hide anything. I gave you the entire proof there, those last couple slides there. So I hope.
But it's true that you don't need a full braiding, right? You only need a half braiding.
That's all I use. All I use is that. And it really is just a crutch to manipulate those things. I guess I'm going to show that slide again.
Yeah, okay.
Yeah, it really is just this crutch to get everything to look the same. It's just manipulating graphs. And that was the way I found it. I couldn't think of a way to do it without ever using braiding. I think, but I'm not saying it. I just couldn't do it. But that's a personal technical problem, not I think a systematic problem. But at most, yeah. That's just half braiding. That's all you. You saw.
Philosophically, as you already mentioned, this is a 1+1 quantum, 2+0 statistical. So you don't need the braiding. The braiding will give you one dimension up.
Yeah. Well, right. I guess, that was a question from before, right? Yeah. So now, of course, a lot of these things have meaningful analogs in 2D quantum systems, or 3D classical systems. So, of course, I guess I can put that on the list at the end. Should have put that on the list at the end too. But yeah, no, I'm very optimistic. That's why that's why I'm just going to write the damn paper now, and I hope that you and others can figure out the more complicated stuff.
Nicely taken. I think Bernard Nam has a question.
Yes. You said all the cases you checked, so you must have done some systematic search, maybe in fusion categories coming from affine Kac-Moody algebras or so. So how far did your search go?
Well, so part of the search is easy because you go look at the this paper by Zhang, Gould, and Bracken, and and then some follow-up papers with the Delius, Gould, and Zhang. And so they did a lot of cases there, and it's the same equation at the end. And then I checked various random cases where the current wasn't the adjoint, they were in the adjoint. And then I checked with known solutions of Yang-Baxter. So what I have not done, because by now the categories have gotten so complicated that it's a real pain, is then go and check that these other ones solve Yang-Baxter. I would be stunned if they didn't, because they're all built on the quantum group. But I have, so I've checked, well, obviously it's the same equation as Zhang et al. So I've checked those, and I've checked some other ones, different representations that don't obey, and blah, blah, blah. So yeah, but I haven't done it systematic. Well, the systematic was done already, and then I did ones on top of that to make sure everything was okay. But it's like, these guys work really, really hard. This is the problem with this thing. You can't escape their hard work, and very easily. I also did these dilute models. I checked those by hand too, where you make the object on each edge not simple, a more complicated object on each edge. Everything I wrote was always a row on every edge, and you can do more complicated things. I checked some of those too. It all works, but yeah, that's why I think rather than check case by case Yang-Baxter, someone should really try to just prove it in general, because I think 90% of the way there, but it does require some thought.
So Chengwei, did you have a question?
Just a comment to John Haas' question. It actually doesn't require many half braiding. It only requires half braiding for the generating object row, namely the simple object row. In the future factory, it's also in the center.
Yeah, that's right. That's right. So there might be cases where you can get it to work. Yeah, that's why I made this comment. I mean, it certainly isn't going to work for an arbitrary object phi in this, but I don't need that. I just need one to get in there. In fact, I think I wrote it, but I didn't say it. There are examples where you can get multiple objects for phi. And this is how you, for the aficionados out there, this is how you get the Ising-Karapin solution by chain. You get this sort of normal fused solution to use the standard nomenclature, but if you use a spin 1 current, and you get the Ising-Karapin by using spin 2. So you can play all these games and they're there. And so yeah. No, I'm very optimistic that stuff like this will work. I haven't done what you suggest, but I'm hoping people will.
So Lena, do you have a question?
Yes, so I would like to continue, ask for details like what Werner was asking. How do you know that your solutions are new? So what kind of invariants are you using? Because those people like Drinfeld and whom you mentioned, they do have invariants, like for example, structure groups and so on. It's do you look what are the structure groups and maybe structure semi-groups?
Well, I certainly don't get any new category. I mean, I always say, for me, that's off the shelf. So I'm not defining any new braiding. I mean, it might be interesting, of course, to start thinking maybe, again, this is something simpler. Maybe one can start to think that maybe there is something new under the sun. So I'm certainly not there. And so that I'm certainly nothing new there. And yeah, so no, it's, the point is people, when things got complicated, people stopped checking brute force Yang-Baxter stuff. So my checking usually is saying, well, I get these Boltzmann weights, and then I go find some paper that nobody cited because it was this nasty calculation from the early 90s. These are always early 90s papers because the 80s had kind of ended, and so only a few really tough workers were still doing this then. And then I go check and say that, if they'd written their Boltzmann weights this way, they would have been clear. But anyway, and then check that my thing's there. And then like I say, I can get examples that nobody's written down. But then I've been too lazy to just sit, because it is not true, because to check that they satisfy Yang-Baxter, that's why I showed that functional relation. I mean, it's just totally non-obvious. And so, yeah, right. No, so I don't think, I suspect if you do anything based on a quantum group, it will at least be nothing new in principle. Now, whether anyone's written it out or thought about it, and maybe this is a lot easier. So I guess you could say this is now a nicer way of writing them out. So it makes it more tractable to deal with seemingly more complicated cases. But I would be surprised if it were anything completely new. But why I mentioned this Hagerup stuff, or the stuff that Zhenghan was mentioning, that will be, as far as I'm concerned, totally new. I'm not aware of anyone ever writing down solutions to the Yang-Baxter connected to any of these more complicated fusion categories, where the braiding doesn't come from some nice quantum group thing. So yeah, so I know, it's a tribute to the spectacular work that was done in the 80s by Drinfeld and Jones, and then the physicists thinking about this. I mean, they did a lot. I could have saved them a lot of time, I think, is basically the thing, but they managed to do it without having this.
Thank you very much. It's very interesting, because actually going back to this work, I've gone back to work of Drinfeld and Manin and Voevodsky, Kapranov, and actually it's so my recent work is complementary to yours. I do have plenty of new solutions of Yang-Baxter, but for me it's more interesting how it's related to physics. It's what we started to do, to look at with people from this seminar. It's actually.
All right, well, good. Okay, I don't know. This is great. Okay, good. So this is now compare the two and see if they're the same thing, or if it's probably more interesting if it's not the same thing, of course. But then maybe I missed something, and there's another.
No. It's definitely kind of different directions.
Okay. Well, good. So no. Okay. Good.
Elena is expert on higher dimensional things.
Yeah. Good. Well, I am not. So yeah, I mean, at least a priori, I'll be optimistic at the moment why you can't use more complicated TQFTs in higher dimensions, find some analogs. And I have some seemingly orthogonal work I'm doing on higher dimensional solutions of Yang-Baxter, Samologikov and Bajanov-Baxter models that are not so far from this story. So that's again part of some grand scheme of things. But yeah, no, I'm optimistic. Whenever anything works out simply like this did in the end, you always think it must work for everything. Life is harder than that, but at least I can be. I'm in the optimistic phase now.
Kengwa, you're still unmuted. Did you have another comment?
No.
Can you think that other new solutions could come from Yang-Baxter relation, not equation?
Well, for example, the Haar group. If we don't take the center, that is not braided. And then I can prove Haar group doesn't have solution of the Yang-Baxter equation, no matter it's parameterized or not.
So without using the center?
Without using center, Haar group has no solution of the Yang-Baxter equation.
That's it. All right, so then you have to use the center, which I guess is not completely surprising, but
yeah, but it has a different type of Yang-Baxter relation. It's the point is, if you take one triangle for the Yang-Baxter equation, you replace that by another triangle. The Yang-Baxter relation means you can replace that by a sum of triangles.
okay.
And Haar group has that property. It's kind of a generalization.
Yeah, well, a comment I remember Anton Kapustin made after I gave this talk at some point was that he said, well, it has to work. And I said, well, God, I'm happy to hear that, but why do you think so? He said, well, it's certainly going to work for anything connected to a quantum group. And I agree with that. And then if it's not connected to a quantum group and it doesn't work, then you would have a quantum group detector, right? Because you would just plug your category in, you'd see, oh, it fails. And thus I know there's no quantum group anywhere that could do this. He said, and I don't believe that that exists, so therefore it must work. I think that's a little bit optimistic, but I'd like that to be true.
So there are further questions. Well, if not, I'd just like to thank Paul again for really wonderful talk, and we look forward to the papers coming out of this. And
yeah, thank you, Nagmir, for nodding. Thank you very much. Well, take care.
See you next week.
All right.